All right. So good afternoon, I guess. So how are you doing? Fine. It's only week 2. You should be doing okay still. If when I ask you in week 10, they'll go, oh shit. All right. So has anybody looked at project 1? Have you made some experiments? Nope. All right. So there is an algorithm that I'll present. We'll talk about index performance. And so you should be paying attention to everything I say in this lecture because it's going to translate directly to your project. So you can ask questions at the end of this if you still have some. Now, it's possible that you might see some strange things, but try to dig them out. If you, there was one thing that came out here is that they see expensive queries for very small or for relatively small percentages with unclustered index. And I'm suggesting to try only with like 1 or 10 records, because retrieving 1 or 10 records should be extremely fast in any case. So if that's not fast, then you have a problem. And then you can work from there. Okay, so I also heard from some of you that maybe the assignment took a little bit more than 90 minutes. Is that the case for many people? So who completed in 90 minutes? Completed in 90 minutes. Who completed in 120? 150? Okay. All right. So who has worked with Excel before? Okay. All right. So it's heavier than I thought. Anyway, I'll be extra careful next week when you have the assignment, the project due. So, I'm gonna try to be very careful. All right. So we talked about the basic things. I'm going to turn on the projector. Sorry. So we talked about some very basic things last Thursday and this Tuesday. Remember, we were talking about indexing, how we implement indexes. We talked about sorting and hashing for query processing. Or more accurately, we talked about sort of how you do sorting and hashing when you have data on disk. And that was the important thing. And we talked about the disk architecture, and the main conclusion of that was basically random is bad, sequential is good, pretty much. Now, there was an interesting discussion just before the class that when you have these new sort of storage stacks that are mixing hard disks and solid state and maybe even some memory, and they completely change the trade-offs between sequential and random IOs, what does the database system do? Can we tune the database system to these storage architectures, or might they be making mistakes? And I believe the answer is that probably they will be faster because the storage stacks are faster, but they might be suboptimal, which is a different story. You might remove some of the bottlenecks by making a faster disk, but you might be able to do even better if you actually went and tuned your database. And there is a thread of work coming out of ITU in Copenhagen and INRIA in France that is doing exactly this. It's trying to look at what happens with these new storage architectures and how should we redefine database systems? How should we redesign, these architectures to make them faster? And of course, some of the sort of big data things that we'll talk about at the end will cover some of these issues. We'll talk about main memory databases, for example, and there will be some interesting things about this once you get there. All right. So now we go into query processing. So we really start applying these things and learning how the database system runs your queries. And this is the goal now. And you can argue that this might be the most important part of the course, because essentially what you'll have to do to make your database system optimal, and this is regardless of whether you're coding the system or whether you're a DBA, is query tuning. Queries are typically the source of bad performance. Now, we'll also talk about recovery and things like this, and tuning that can be very important. Tuning locking, for example, can be really important, but mostly people mess up with the queries. And that's part of the, for those of you that were in the course, I think that was like 1/3 or more of the database administrator's task list was to help the coders to perform better queries. Now, what happens when you run a query is basically 3 steps. The first one is that it's parsed, so you quote your SQL. It's parsed, and there are some lookups to check. This is where you get the errors, like the table doesn't exist in the database because you had a misspelling, or something like this, or you have the wrong column, or something wrong with your syntax. And this is where you get those errors. And so there's some lookup into the system tables to figure out which tables exist, which index exist, and so on. Then what the parser does is basically create a plan, a query plan, that is very simple, probably very inefficient. Might typically be something like a cross product or a simple join. And then this is sent to the optimizer. And this plan is basically relational algebra, somehow augmented relational algebra. Then this gets sent to the optimizer, and it turns out the optimizer is pretty good at algebra. So it knows things like transitivity of operators, and what's the other thing where you can switch them around? Well, how's your algebra? I completely forgot. When you can swap to the order operator to the multiplication, it's commutative. Would that be it? All right. So this optimizer is very good at this. And it's very good at this so that we don't have to be so good at it. But it's good to know. And what the optimizer produces is basically an optimized plan. Now, I don't say optimal, because it's not necessarily optimal. The optimizer has to work with some statistics. How many different values are there, for example, in an index? And based on the statistics that it sees and the operators that you want to perform, it's going to make a fairly good guess at what's the best way to run the query. But it might fail. It might assume that all the values are equally likely, whereas you actually asked for something that doesn't exist. So there might be some things that it just gets slightly wrong. The goal is basically, you'll see when we talk about optimization next week, is that the difference between a bad plan and a decent plan might be 99%. And then the difference between a decent plan and the best plan might be very little. So it's trying to get very close to the optimal. And this is why we call it optimized. And it's sometimes optimization is called disaster avoidance. Just want to avoid the disasters, you want to get something that's decent. And once you have this, which is another relational algebra expression, sort of augmented with how to do this physically, then you send this to query processing. Now, we won't talk too much about parsing. It's basically, if you take compilers, which I highly recommend, then you learn about parsing. We'll talk about the optimization next week, and now we're going to talk about query processing, and we'll do some basics first. And if you have any questions, then feel free to ask. So this is sort of an example query plan. It's basically a tree of operators. You can think of this, you could write this as an algebra expression. It's a project of S name applied to selection of rating greater than 5, applied to the join of two relations, one of which is selected from. And so it's drawn like a plan because it makes it easier to visualize what's going on. If you're working with SQL Server and you have a query and you hit Control L, I think, you will get a plan like this. You'll get a tree that looks very similar to this, and you can look at the operators that it has decided to use. So you get the optimized plan. Now, sometimes, and you can see that what we have here is things like when is it executed. So this says it's on the fly. We just get tuple from here, from the join, and then we say, does this tuple satisfy rating greater than 5? On the fly means there's no disk IO. It's just as the join produces tuples, we check whether the rating is greater than 5. For tuples that satisfy that, we remove the column, all the columns but the S name, and then we output. We also have this which says this is an index nested loops join. We'll talk about what that means. It's a particular join algorithm. And so this is getting into, it's not just the algebra, it's also saying, how do we do this? This case, it's saying, well, we're going to use a hash index, which I've told you that doesn't exist, but for the sake, it might be a B+3 index. And this one is saying we're going to use the index. That means we're going to use the index to look up all the boats that satisfy this criteria. So you can sort of read from this plan how this is going to be executed. Basically, we're going to find all the reservations for boat 100. Then we're going to, for each of these, look up the sailor that reserved this boat. And then we're going to see if the sailor has a rating greater than 5 and project the sailor name. And that way we get all the sailors that have reserved boat 100. You're following? Okay. And that's, this is the way to read the plan. Now, the plan could have these relational operators that you know and love or hate, I don't know. Selection, projection, join, test the set algorithms. But then in the algebra that we talked, we didn't talk about aggregation and so on. So there's basically some augmentation. It's sort of an extended relational algebra that has these aggregations that again produce tables, but they have a very different form. And then we have these physical operators that are basically saying, well, for join, for example, we need to specify what kind of join this is. Which algorithm are we using? Because they will have different performance characteristics. Might be sort merge join, which could be good if you have indexes and so on, if things are sorted. Could be hash join, which is good if one relation is much smaller than the other, and so on. So that's what you get in the tree. It's what kind of algorithms are you doing. Disk access could be either a file scan or an index scan. So we could either just read the whole file, or we could use an index to read only a part of the file. And then we might add sorting if we need order by, then sorting might be the last thing we do, or we might have it somewhere in the middle, depending on the optimizer. So that's kind of the operators that you'll see. With me so far? Now the interface that we do, or the way to code this, is basically a class tree of a type iterator, where each iterator has a very simple interface. It's just to open the iterator, get the next tuple, or close the iterator. And that's all you can ask. Now, underneath the main class, you might have binary operators, you might have selections, projections, and so on. But they all basically do this. You open, you get all the tuples from it, and you close. And you'll see probably at the end that people are actually criticizing this model. But for now, this is how things are implemented typically. So if you think about this very simple model, if you wanted just to read all the tuples from a relation, how would you do this? What would open do? Basically open the relation. You sort of, if the relation is stored in a file, you open the file, you have a file pointer that you need to store, and that's it. That's open. Next, read one tuple from the relation. Return it. Probably the actual implementation would read a bunch of pages and then you produce tuples from the pages. But that's the simple thing. Then when you're done, when you get an end of file, what you do, you close. Now, if you have a selection, so you have a scan at the bottom, and then you have a selection for, let's say, rating greater than 5. How would you implement selection? Selection is an operator that has one input, right? It's, the input is this. It's a subtree underneath the operator. When you open a selection operator, it basically calls open on its child. That's it. You're done. Close, same thing. when you say next, it will call the scan underneath, ask, give me a record. Gets the record, checks, does the satisfy rating greater than 5? If it satisfies it, return it. If not, get the next thing. If you run out of things, just send the file up. Can you visualize how you'd program this? Based on your experience with data structures and so on? It's a very simple interface. Now, hash join, we talked about hashing a little bit, but not too much. So we'll do this now, and then you'll completely understand this once we talked about hash join. But basically, a simple hash join would build a hash table on one relation, and then use the other relation to probe the hash table and look up. And so an open would actually open the entire, so you have a hash join here on, let's say, you have a hash join here on product and join sales. Sales is very big, product is very small. So you open the products table with the open call. You ask for next, and you put that into the hash table. You ask for next, put it into the hash table, and so on until you complete it. And then you have a hash table. And then you return and say, I'm ready. That's the open call. It constructs the hash table. Then when somebody above you, that could be, for example, a display operator, says, I want a record. Then you say, okay, I'm going to get the record from the sales table. I'm going to probe the products table. Yeah, the hash table for the products. Yes, exactly. The hash table for the product relation. And since it's probably a key foreign key relationship, we're pretty much always going to find the record, right? If it's not a key foreign key relationship, we might not always find the record. But we'll find the record, we'll put them together, return them. What about multiple records? So if it joins to multiple records, in that case, basically, we would need extra state. So if it's not a key foreign key join, we might have extra record. In that case, we need to keep track of how far we are into the hash table to look for matches. So we get the bucket, we have to scan the bucket for matches. And so we need to keep a track of the scan so that when we call next, we continue with the scan where we left off. So we just need to keep enough local state to be able to continue where we left off. And this can be, in the simple case, it's a hash table. In the more complex case where we might have many-to-many joins, then we need the hash table and the scan pointer saying where we were last time. So the hash table itself might be changed or it might not be changed regardless of whether you have one-to-many, because that's going to depend on how many things are in your hash bucket. And so if the hash bucket overflows, then you have chaining and so on. So you will need to worry about this basically regardless of whether you have many-to-many or one-to-many. But when you have one-to-many, you can say, once I've gotten a relation, a record here, and I've found the match here, I can basically just get the next from here. So in that case, all you need from local state is the hash table. But if you might have, basically you have a bucket that is changed somehow, and you might have matches here and here and here and here, then you basically need another pointer saying, well, this is where I got the last one. And so when I get the next call, I'll go from there and find the next match. So again, it depends on your. Very good question. So we're not going to be implementing this as such, but I just want you to sort of have a rough idea of how this would be implemented. And the nice thing, this extends very nicely to distributed processing, and you can implement basically anything with this kind of model. So that was sort of a brief thing about the architecture. Then we talked about this actually. So this is a slide that we had in a slightly different format last Tuesday. Basically, we've covered the basic techniques. We can read everything. We can just open a table and just read it all. That's one way to implement query processing. Sometimes we can avoid reading everything by using an index. Sometimes we can sort things and it will be faster, and sometimes we can hash things and it will be faster. So these are the options. And then for all of this, for when we're reading from disk, we have this I/O optimization that we talked about. You can use blocked I/O to reduce the random reads. You can use shadow blocks to read ahead to avoid waiting, and so on. And those are completely general. All right, so we'll talk about selections, then go into joins and sort of set operations, and then summarize. So we'll probably get through the selections now, and maybe start with the joins a little bit, and then we'll continue joins after the weekend. And keep on asking questions if you have any. Okay. So you remember what a selection is? It's basically checking whether records satisfy a criterion. And if it satisfies, it goes into the result, or if you have a complex tree somehow and there's a selection in the middle, it's basically goes up in the tree. So it doesn't necessarily go to the result, but it goes into further processing. Might be a join, might be another selection, might be a projection. So how could you implement selections? Well, one is basically to read the entire relation and then apply the selection. So you just have you might say you have a scan, and then you have a selection operator. What's the cost of selecting records this way? What do you need to do? You need to read the entire table. So if the table has m pages, the cost is m, modulo all the optimizations that you can do. And for this, sorting and hashing don't apply. I mean, this is basically just read everything, right? Now, then you can use indexes, which in many cases might be better. And remember, they can be clustered and unclustered, and then in some cases we might actually have many indexes on the same table, and we'll look at how we can use that. So, and I'm going to start with simple conditions because those are typically what you have, and those are easier to talk about. So if you have an index on the column that is in the selection, so you have some kind of column, and then you have some operator, might be equal, might be greater than, and the value. How would you use an index to answer this? And I would say let's start just considering the equality. How would you use an index to satisfy or to answer a query like this? Give me all the records that satisfy that where the column is equal to 10. Well, in this case, I would actually want the whole record because there's no projection, yes. But yeah, only this column is indexed. So you will have to read something from disk. So the point he's making is that if we are only asking for this column, then we might actually just read from the index. But in any case, what we need to do is to go through the index, find the leaves that have the pointers to the record, and go and get the record and bring that into memory. All the leaves, well, yeah. So let's say the simple case, we might have ID equals 10. So ID is a key, it's going to be one record. So in that case, it's probably a B plus tree. So we have these, tree structures here. And so what we do is we go to the root, we search, remember how we did this? Scanning for the value, we go left and we go right. This is a leaf, and that one has a pointer to disk. And so we read that page and get the record and return it. If we had a hash index, remember how we did that? We basically did the hashing, found the bucket, retrieved the bucket, found the pointer, retrieved the record. So that was even simpler. There's no navigation. The navigation is in the calculation. So if we have something more complicated, let's say that you have in the sales table, you want to find everything with emp ID equals to 10. So everything that employee 10 sold. So that might be a lot of records, right? How could you do that? And let's say we have an index on emp ID. And that means all the emp IDs 10 are going to be together. So we have kind of a range. It's actually the range of one value, but it's basically the range in the index, range of leaves. So in that case, we just find the first entry, and then we scan. And remember, we had these pointers in the index that we could traverse to find it. And in each leaf, there will be a number of pointers that we have to go to disk to retrieve the records. So what is the cost of the index going to depend on? I mean, if you think about it, well, it's going to depend on the index type. If it's a hash index, there's one kind of cost. If it's a B+3 index, there's another kind of cost. If you have, if you had something entirely different, there would be a different cost. It's also going to depend on the number of records you select, right? So in the latter query we had to get a bunch of leaves. So that's already a cost. Yeah, exactly. So when I say record selection, that's exactly what you mean. It's how many are matching the condition that you have. And then it's going to depend on your clustering, right? So you remember how clustering works? If it's clustered, then everything that's together in the index is going to be together in the table or in the file. If it's unclustered, then you get randomized. They will be randomly scattered throughout the file. Yeah, so you're asking the optimization. So the optimizer is basically going to look at what are the indexes I have, what are the types, what do I estimate the cost to be depending on clustering and so on, and then it's going to make a choice. Then you have the implementation, which hopefully would do things like, when you have a range, go to the first one and then just scan rather than going repeatedly down and things like this. But the optimization is basically in the choice of algorithm to use. Good question. So these are the three costs. The index type, or the three things that impact the cost of retrieving records from an index. So what kind of index is it? How many records are you selecting? Or how many things satisfy your criterion? And then your clustering. All right. So how is the cost going to depend on the index type? What do you do to answer a query with a B+3? Retrieve the root, right? Do some things. Find the pointer, traverse it, retrieve the next node, and so on until we hit a leaf. Hash index, you do some kind of hash function, and then you get the leaf. A good hash index will be mostly a single layer for the leaf, but sometimes, on average, you might get something like 1.2 IOs. This was a fudge factor that we had. So sometimes some buckets will be less than full and others will be slightly more than full. And in that case, you have 2 pages, and on average, the number of pages is 1.2 with a good hash index. So this is why we called this the fudge factor, remember, in some formulas last time. So So how many IOs do we have in the B plus 3 index? Something log n, like it's basically the height. So there's some kind of fan out. We call this order or D, or I forget what it was, maybe D. And then of the number of records. So that's the cost of this. And again, as we talked about, this is going to be 2 to 4 roughly. So at the end, you have to add for retrieving the record, but that cost is actually going to depend more on clustering. So we'll consider that when we do clustering, because if you have one record, it doesn't matter, but with many, you might be. So, and then you can, with a highly used index, you might assume that this is in buffers, and maybe even this one is in buffers all the time. So you might say, okay, so it's going to be like 1, 2, 3 IOs at most, or maybe 1 to 2. So that's sort of the assumption that the optimizer will do. And that's the cost of the index type. This is the way it depends on this. Now, clustering. So to decide the cost based on clustering, what do you need to know? You need to know how many records you will retrieve. This is called selectivity. How many records are going to be in your answer? Can you know this for sure? Excuse me. Through the catalogs, you can often get a very good idea. So, for example, if it's a key, how many can you have? If it's a key and you have an equality, how many are going to be in your answer? 1 or 0, but it's one lookup. So if it's let's say that it's an equality on emp ID for sales relation, how could you estimate how many things you will have in your answer? Number of records, some statistics. What statistic could be good? Sort of quick one. How many employees are there, for example? Or because if you assume every employee can sell equally much, then you can just say number of records divided by number of employees. Or you might say, well, the guys that sell are actually the sales personnel. So in that case, there might be. So for example, there might be in the catalog statistics about, what is the number of emp IDs in sales. And in that case, if you have that, great. You can do a fairly good estimate. Now, when we get to database tuning, we look at the fact that the distributions are not always uniform, right? Salesmen or salespeople don't sell as much as a rule. Someone will sell a lot and others will sell less. And not necessarily because they're bad, but one of them might be selling huge projects where one sale per year is really, really great and saves the company. Whereas somebody else is selling lots and lots of small stuff where, it's high throughput. Okay, so we need this. We need the selectivity. And let's call this R. It's a relation, it's a number of records for now. Clustered index, how many IOs will we perform to retrieve R records? Depends on the size of the record, right? Correct. And how would we know the size of the record? We could say, for example, page size divided by record size. Is that correct? Because that tells you how many records there are per page. Is that? And then divide the whole thing by R. Number of records per page divided by number of records in the answer. And that's a fairly good estimate of how many pages you need for a clustered index. Clear? If you're losing the thread, then tell me. So let's give a specific example. We have a page with 4 records. These are pretty big. Page is 8K, record is 2K. So this thing here is 4. And let's say that R, you estimate that R is equal to 8. And so in that case, we actually messed it up. And this is maybe why you're confused. So it has to be R divided by page size divided by record size. So if you were confused, you were good. So, all right. So that's basically, in this case, 8 divided by 4. And it's 2 pages. With me so far? All right. Now, is this always going to be correct? This very simple estimate? And I can think of one sort of simple way that it might be wrong, right? When your first record is actually here. So you get something like this. So your estimate is slightly off, right? It should be 3. The correct number is 3. Just because you didn't hit the page boundary correctly, the estimate is slightly off. Now you can get some benefits with doing like a ceiling, but even in this case, the ceiling is actually 2 and you were slightly off. But 2 versus 3, again, remember this is disaster avoidance, 2 versus 3 doesn't matter. Now, if the clustering isn't perfect, that's kind of a worst case, right? So in that case, my drawing skills are immense. If the, you might be getting something like this. So if the clustering isn't perfect, then it might be slightly off. But we'll assume basically perfect clustering and horrible clustering. But you're with me on this. So basically we take the number of records that we expect to get, and we divide by the number of records per page. And we say that's the number of pages we read. That's the number of IOs we need. How about unclustered? What assumption can we make about the reads for unclustered index? Yeah, 1 IO per record, so we basically get this, right? If that's the number of records you get, then that's the number of IOs we get. So that's sort of, it might be slightly better, especially if R is large, then you might be able to save some. But this is sort of a pessimistic estimate. Clear? So you basically have this summary. You have, based on index type, you might have 2 to 4 IOs. Based on if hash index, you might have 1.2. Number of records we need to know, and we'll talk about in the query optimization part how to estimate this in more detail. And then, so we need to figure out the number of records. And then for clustering, if we're retrieving 10% of a relation for a clustered index, we actually have 10% of the IOs. For an unclustered, we just have the number of records. We assume that buffering doesn't help and so on. If you have enough buffers, if the table is R pages and B is greater than R, then basically you will have to read each page only once, right? And then it will be in memory. So in that case, you actually, even though R is greater than R, the cost will be basically R. If, however, the table is much larger than in memory, then probably it's going to be the small R, not the big R. So this is a graph of the real cost. This is actually a fairly old graph on some really bad computer, but this is kind of what you have to do in your first assignment. You have to produce a graph like this. Now, this is an old enough version that basically if I had continued to force the system to use an unclustered index, it would have gone up like this. What you're going to measure now on SQL Server is probably something like this. And I actually want to let you measure this before I tell you more about why. There is some caching, but let me see. Actually, let's talk about the next algorithm before we go further. So, but you will see something like this. You will see very bad behavior, and then all of a sudden it actually jumps a little bit probably, and then it's sort of slowly decreasing. Now, there are ways to work better with unclustered indexes than just reading everything. And one way is called reordering reads. So, and the algorithm there is basically, you just go through the index and you find all the leaves and all the pointers to disk that you should be retrieving. And you take that into memory. You're still not getting any records. And then you sort these records based on your page ID. And then you start reading. And so in some cases, you might be able to get some kind of sequential behavior if you do this. So I actually had an example of this. So did you see the examples? It's in a zip file basically under lectures. So all of these examples are found there and you can look at them. So this one, so basically if you had an unclustered index and you had to read, then you would have to read each table page once. And here we are scanning an index and you can see we have the first record from page 20, the next one from 30, and then the second one from page 20. And if we don't have enough buffers, then we'd have to read 5 basically. Right, page 20, sorry. See the buffer here? So that's if, assuming we don't have enough buffers to store everything. So we spend some IOs. Now, if we do the better usage, we just find the leaves and we store them in memory and we sort them. And then we go and read the records. And now you can see that the reads to page 20 are adjacent. And so they will be served in the same IO. And then you have to read. So if we go back, if we go, sorry. Save. If we go back here, you think you might have an explanation for some of this behavior? So you can see it sort of goes from the unclustered, really bad performance up. Okay. Back to normal. Yeah, so it's basically shifting from this is basically still doing one IO per each, and then all of a sudden it shifts a little bit. And in that case, because you're already with 20% of the relation, you're probably reading most of the IOs anyway, most of the pages. And so you're just gonna, the performance will decrease slightly because you have to do more work to, process the CPU and so on. But the IOs you won't add too many IOs after this. Now the jump here, you can figure out. I'll leave you to figure this out. You probably see this jump, and we'll just have to try to understand later on why. Why is this jump? But it's interesting. And so in previous times, I asked people to stop measuring unclustered here. Now I ask you to measure unclustered all the way through because of this. So let's take a break now, and then we'll go to more complicated stuff after the break. All right. So during the break, we actually, based on the first numbers, we kind of verified this particular behavior here, where we have a slight drop and then slowly increasing performance, and actually maybe more accurately, this would be something like pretty much flat at the end, because there's no more IOs and CPU is not costing that much more. Right. Okay, so that was the reordering reads. And this is basically how we use an index when you have these simple conditions. I mean, if you have something like a range, we go here. I mean, this is basically looking at ranges. If you have something like, you know, greater than, you might say something like date greater than 2013, and you've been in operations in 2012, then you expect roughly half of, or maybe 1/4 of your relation, and then your R is basically 1/4 or whatever. And so in that case, you might be here. And then optimizer would use a formula for this and basically figure out, hey, would be great to have an unclustered index. Or if I don't have an unclustered index, then I'd better just scan everything, because the clustered index is not going to help. The unclustered index is not going to help. It's going to be more expensive. But that's the job of the optimizer. Okay, so basically, if we have a hash index, because we have a hash function that takes as many inputs as there are search keys. Remember, what's a search key? It's what you use to look up the index. It's the columns that are indexed, basically. For a hash table, if you have an index on A, B, and C, then the hash function will be on A, B, and C. We'll take 3 inputs and do some calculations. And so remember, hash is only good for equality, because you need to find the precise bucket and you need to scan that bucket. And so in that case, if you have a query saying, A equals to 3 and B equals to 5 and C equals to 10, then you could use a hash index to answer that. If you only have the first 2, you could not use a hash index, right? Because you cannot apply the hash function to a value that you don't know. Now, how is this relevant? Well, for hash joins, it's typically on an equality. You only have hash joins on equality. If you don't have equality, then you don't have a hash join. For the B plus tree, however, it's basically more flexible. So assume that you have an index on A, B, and C. What does that mean? It means basically that at the bottom of the tree, you will have first everything that has A equals to 1, A equals to 2, A equals to 3, and so on, right? Because that's the thing you sorted on first. Within the A equals to 1, you will have B equals to 1, B equals to 2, B equals to 3, and so on. And then for that, you have B equals to 1, B equals to 2. See what I mean? And then between that, you will have all the different values of C. So if I ask a query on C, let's say I say C equals to 3, well, I will find that here and here and here and here. See what I mean? Everywhere. So the index won't help that much. Maybe I could actually read the index, and if there are very few values of C equals to 3, then I can just retrieve those records. So it might actually be faster, but it's less efficient. But if you have a prefix, then this is great. Because, for example, A equals to 5. Well, okay, let's go with A equals to 1. I know it's all going to be here. And even better, because I have B equals to 3, I in fact know that it's all going to be here. See, prefix is good. And this is why column order in the index actually matters, can matter a great deal. Mm-hmm. Okay. So if okay, so yeah. So the question is, if we have an index on A, B, and C, we have a developer that doesn't know the order, and so the developer might therefore do some suboptimal things. And the question is, does the optimizer account for this? If you have, let's say your developer just asks for everything with B equals to 3. Well, that's actually what the developer needs. The developer doesn't need A equals to something and B equals to 3. It just needs B equal to 3. So in that case, it's kind of the job of the optimizer in that case would probably choose not to use the index. We'll go and just scan the entire relation. And it's actually the job of the database administrator to provide an index if that's a very important query. Yeah, okay. So if the developer somehow said A equals to 5 and then maybe somewhere else say B equals to 3 and then A equals to 5, you would expect the optimizer to figure this out and do the sort ordering correctly. Do the column ordering correctly. Because basically, because you would find a plan where you were doing first A and then B, that would be cheaper than the other one. So the optimizer will produce a lot of plan and try them out and do the cost computation, and probably a plan that will do A and B together and first A will be less expensive. So that's why the optimizer would probably choose that. A good optimizer would. A good optimizer would. And then, of course, the extreme case, if you ask for D equals to 3, that's completely useless, right? You just have you can argue that if you ask for B equals 3, like I said, you might scan the index and just like with the reordering, keep track of all the pointers that point to B equals to 3 and then do the scan. So you could argue that this is possible and some good optimizer would choose that, or good system. But the prefixes are better. They're the easy ones. So for example, there's a system, sort of a business system that basically can store many companies in the same database. And so in that case, there's always a selection on company ID equals to something. In any query supplied to the system, that's always there. And so for that, basically every index in the database starts with a company ID. Because you will always have this. You're always asking for something specific to a particular company. So that's typically a clustered index, or you might partition or something on this. All right. Now, what you do if you have multiple indexes that might be useful. And so we sort of do two cases. One is when you have only and, so this is a conjunctive query from your algebra courses, from your discrete mathematics, or you might include some ors, in which case you have a disjunctive query. So if you have a conjunctive query where you only have ands, then there's sort of two methods to use many indexes. One is to say, I'll just look at them separately and just figure out which one will give me the best performance. So for example, if you have a query on ID equals to 10 and salary greater than 50,000, something, or 500,000. And you're looking at the employee table, and you have an index on ID and you have a different index on salary. Which one will give you better performance? Likely. Probably, because this is 0 or 1. This might be many, but the answer will always have a 0 or 1 record. So in that case, you would probably end up using this index. Doesn't matter whether it's clustered or not clustered because you're retrieving one record. And so just go and get the record and you check. And so it's very simple for this case. This would be the best way to do it. Alternatively, you might say, well, I'm going to get all the records, I'm going to get all the pointers to disk or the record IDs from each index, and then I'll do kind of a merge or I'll do an intersection or something. That would give me all the records that satisfy all the conditions. So it actually shouldn't be a union, it should be an intersection. Yes, that's after you get the records. And you could do this with a hash table or something like this to find the intersection. Yeah, basically, so let's say in the previous example, ID equals to 10. The first one will give you, let's say, record ID 200. The second will give you record IDs, 150, 190, 200, and so on. And so then you do the intersection, and you find out that this is in fact the only record that you need to retrieve. If you had more cases, then you might find lists like 150, but then 160 and 161 and so on, and eventually 200. And so in that case, you would get this and this, but not this one. So you just do an intersection. This is basically intersection of the record IDs, which are pointers to disk. So we talked about this page ID and the slot or something like this. Yes, exactly. And it's basically unique identifiers that go directly to disk. And so this is very similar to the reordering that we had before also. So you're just getting the IDs into memory, selecting the ones that apply, and then getting them. So it's kind of a similar approach. And if there are conditions that are not reflected in an index, you can just apply them later. So a good optimizer would consider both of these. Not so good optimizer would probably just do this. And again, I mean, of course, you have to have this implemented so that the optimizer could consider it. But sometimes it could be better. If you have, let's say you have a query that has something like salary greater than, let's do 300,000, and gender equals to female, and hobby equals to something. And so you have many conditions, but each of these conditions might be not very selective, right? Because gender, for example, will give you on average, half the relation. Salary greater than 300,000 depends on your company, but that might give you a lot of things. So each of these is kind of a bad condition, right? It will give you many, many records. But if you do the union, if you do the intersection, then maybe there's only one person that is female, has this salary, has this particular hobby, and so on. See what I mean? And in that case, this would be a great method, because the number of IOs that you have to apply would be small, whereas if you did any of the others, you would probably actually end up with a sequential scan of everything. Because using an index to go for gender typically doesn't make sense. Like I said, in extreme cases, in IT companies, unfortunately, sometimes it might make sense on one particular, but this is very unfortunate. I have to say, it's really sad. Anyway, but you see what I mean? When you have many conditions that each are not very selective, but together they're very selective, then this would be a good method. Right. So if you have an index on a selective condition, the first method is good. When you have no index on a selective condition, but together they might be selective, then the second method would be good. So again, what we need to be able to compute the reduction factor for each of the conditions. And that again goes to the statistics. We need some statistics on how many values are there and so on. And then sometimes there might be dependencies, between conditions. And so, you might have, for example, salary and age in many companies would be kind of related, right? Or at least the amount of time you work there. You might have some kind of, some kind of distribution like this. And so in that case, the reduction factor of one times the reduction factor of other would give you the incorrect result. Basic statistics. You need sort of independent variables to be able to do the multiplication of probabilities. So that's another important thing. So that was the conjunctive. When you have only ands, then you can do this. When you have some ors, what a good optimizer will do is basically convert the thing to what's called a disjunctive normal form, where you have conditions that have only and then ors between them. So a bunch of conditions with and, or another set of conditions with and, or another set of conditions with only and so on. And this is what they do. And then they would basically go and say, okay, so what's the best way to do this particular thing? If it's an index, good. Next, this one. If it's an index, good, and so on. Now, if one of these says it's best to do a scan, then it'll just scan everything and compute all the conditions on the fly. See, it doesn't help. If I already am scanning the relation, it doesn't help to be looking up an index additionally, right? I might as well just do the whole thing at the same time. But if it comes out that, scan is equal to X, and this is like, 1% X, and this is 5% X, and this is 10% X, then I would actually go and do that. If I find that this is, so let's do another number. This is 30% X, this is 40% X, and this is 50, what do I do? I just scan. Now, most optimizers, if they have something complex like this, they will actually just say, shit, that's complex. I give up. Let's scan it. That's a typical way to do it. And if you have a system in early stages of development, then this would be pretty much guaranteed. That's one of the things that people look at late in the process. Optimizing joins is much better. But basically, you could do something like this. Right. So you can simulate the optimizer. Shit. So that was the selection. Any questions so far? Yeah, so if you have a disjunctive, basically, so I should actually erase some of this. So we could go back to the normal form here. If it pays to calculate each of these individually, if that's cheaper, then what you do basically is you do this, you do this, you do this, and then you do union, exactly, to compute the final result. Disjunctive normal form. So it's basically at the bottom you have ors, and between the ors you just have ands. So, and you can basically convert any formula to that normal form if you wish, and so it's possible. But again, you could try this potentially with some combinations if you are careful to make the C's selective, where it would really pay to use an index, and you find a sequential scan, then the optimizer is just surrendering. That's how you would test this. Just make something that you know will be very cheap, but it's complex. So give me this and this and this, or give me this and this and this, or see what I mean? And you know it's going to be very selective. All right. Other questions? So again, this picture here, that's really the key. This is why we're learning about indexing, because we need to know this. It helps to explain a lot of things. It helps to explain, you created your wonderful index, you run your query, the index isn't used. Why? Because your query is selecting a fair chunk of the relation, and it doesn't pay to use the index. Another reason could be that you defined the index incorrectly. You did something with a column, or you added a column that is not used, or so on. So that's another reason why it must be used. But typically, and I've literally had this complaint: why is the system not using my index? And the guy was somewhere here, and it's just obvious. It doesn't pay off. It also, and you remember, you can only use one clustered index, right? Because you can only sort the relation one way at each given time. What does that tell you? Well, you need to do it carefully. You need to decide what's your clustered index. Again, many systems will just say your primary index, if you don't do anything else, is your primary, your primary key is your primary index. It's your clustered index. But you should decide whether that's the appropriate behavior. If you have a lot of scans, if all your queries are either equality on something like ID, or some range on, let's say, salary, what is the best clustered index? Probably salary, because this one can be answered very efficiently regardless of whether you have a clustered index or an unclustered index. And yeah, and salary is a range, so you might be expecting to be in this kind of 20 to 30% or something like this, and in that case the salary might be a good choice. Now, if the ID one is being asked 99% of the time, the other one 1% of the time, then you have a different trade-off. But if this one is common, then you might consider using your clustering to do that. This behavior here, again, is it's interesting. It still doesn't help. It's an algorithm that will reduce the impact of making the incorrect decision, basically. See, if the system accidentally uses an unclustered index when you are really selecting 30% of your query, then this will actually reduce the impact of that. Selective, yes. This is actually a very good point, and you'll get to this in the database tuning part. Yes, it's actually exactly telling you this. If all your queries are in the range 30 to 50% or something, it's even, this thing depends on your system, could be even as low as 1%. Don't make an index. Now, there is an exception to this, but generally speaking, you don't make an index, because even if the system used it, it would probably be a mistake. And you run the risk of the system using an index it shouldn't use. So it's a very good point. Now, there is an additional thing, is that when you're inserting things, you need to maintain the index. So in that case, you might have an index that is only costing you. It's only overhead of insertion and no benefits from searching. And in that case, that's a very bad trade-off. Now, what's the exception to an unclustered index that might retrieve more than, that where you might want to be here? We talked about this a couple of times already. Covering index. Why is it okay to have a 50% selection on a covering index? Unclustered covering index. Do you remember? Do you remember the definition of a covering index? It has all the attributes you need to answer the query. So it doesn't mean you don't have to go to disk to get the actual the records. And in that case, you're just reading the index. You're not paying the unclustered I/O. So a covering index, it's basically like a clustered index. It's really good for performance. Bad for maintenance, because it has many columns, and so you need to maintain it for any updates. But for queries, for large queries, things like this, covering index would be good. It's basically what it covers the query. This is what we assume. It covers a particular query. And so if you have, let's say you have a very common query, select ID name from blah, 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 where salary, something like this. Well, if you do salary first, which is the condition, and then ID and then name, you could use this index to answer the query. Even better, if you don't have a name, then that index would be sufficient. And that's actually very efficient, because this would be 4 bytes and this would be 4 bytes. So it's a small index. This one could be a little bit larger. But the covering index, that's an exception to the rule that you don't create unclustered indexes for large selectivities, because that handles large selectivities very well, because you don't pay the unclustered I/O. Yes? In real life with big tables, you're usually only querying. Well, so there are kind of two things. in the traditional OL online transaction processing, where you just you have somebody standing in line in your store and doing deet, deet, deet. That's very small things. But then you have the manager in the back doing some kind of reports, and if that goes to the same database, then you have very large queries. That's when you get the huge selectivities. Yeah, right. Yeah. So relatively last week compared to the last 15 years that you store in the database, yet that's a fairly small portion. But for a large company, it still might be a significant query, and it might actually sort of interfere with your transaction processing also. So, but in terms of this, in terms of the proportions, then yes, you might, even a fairly large query might be in the range of 1% if you have a huge table. Are you usually using the same database for analyzing? For a big company, no, you would typically use a different database for doing that. But there's always going to be some reporting of up to data things that will happen. So there's always going to be some kind of scans in between, but typically, no, you would take the really big reports and put them to a separate data warehouse. Yeah. More questions? This is fun. All right. But again, so remember this picture, and now the first part of the project is to look at the database architecture of SQL Server. It actually differs slightly from what is covered in the book. So there's a clustered index and an unclustered index, but what is stored in the clustered index, in the unclustered index, is slightly different from what we have described in the book. And so the first part is actually to discover this difference, and then you have to remember it. And because there's the occasional query where it really makes a difference on how you could answer the query. So I'll let you figure this out, but there is a real difference from the description in the book. And so the first part is actually to figure this out. Now, the normal thing people have done in the past is to look the help online, copy what's relevant into the report. I don't recommend this. I actually recommend understanding and then writing it in your own words and trying to make your own picture if you want, or just describing it, because I think in some cases I've seen like 80% of the reports had this, and then I asked a query directly from this topic, and 80% of students got it wrong. And you can guess the correlation if you want. So I really recommend to understand the trade-off, to really dig into what's there and why is it different and how is it different and how could that impact things. And it's more important to me that you write your own description. It will be better for you to write your own description than to do the copy-paste. The copy-paste, of course, is beautiful text, but it's not really a good way to do this. And again, I'm not kidding. 80% of my class has gotten the question directly from this project wrong. Which they all had perfectly in the report. So I recommend to learn this. Yeah, 80%. We don't even have that many in the class. How could that be? That's a good one. All right. So, all right. I think we'll just keep the joins until next time. You look like you're a little bit tired, and so we'll do this. It's a good thing to digest. But so we have a few minutes, go and look at the project now. I would recommend to do this, and because you're fresh. Indexes are fresh in your mind. Look at the project. All right. See you Tuesday.